Combinatorics, Lecture 4, Pigeonhole Principle and Binomial Coefficients. Let us start with the pigeonhole principle. This principle asserts the following. If n items are put into m containers and n is strictly greater than m, then at least one container must contain more than one item. So this principle appears as early as 1624 in a book attributed to Jean Lerichon. And it has many different names. It is also known as Dirichlet box principle or Dirichlet's drawer principle. And it admits various generalizations. One of them, which we will use, is the following. If n items are put into m containers, and n is strictly greater than k times m for some positive integer k, then at least one container must contain more than k items. Let us look at some examples which illustrate the use of the pigeonhole principle. Example 1. If there are 17 students in a classroom, then at least 2 of them have birthday in the same month. Indeed, our containers, our boxes are months, so we have 12 months, and our items are students, we have 17 students. As 17 is strictly greater than 12, we have the claim it follows directly from the pigeonhole principle. Example 2 shows that there is a number of the form 5, 5, and so on 5, and then 0, 0, and so on 0, with at most 200 digits, that is divisible by 123. So here our containers or our boxes are non-negative integer remainders when divided by 123. We have in total 123 remainders, 0, 1, 2, and so on 122. Our items are numbers of the form 5 or 55, 555, and so on, numbers which have at most 200 digits and all digits are equal to 5. So we have 200 numbers and 123 containers. By the pigeonhole principle, there are at least 2 numbers of this form which have the same remainder when divided by 123. So we subtract the smaller number from the bigger number, so we take 2 numbers different with the same remainder, we subtract the smaller one from the bigger one, and we get a number of the form 55555, 00000, with at most 200 digits, that is divisible by 123. Here is yet another example. In a cocktail party with at least 2 participants, there will be 2 participants with the same number of friends. So here we assume that being friends is a symmetric relation. If x is a friend of y, then y must be a friend of x. So here our items are the participants. So we have k items, where k is a number of participants and it is greater than or equal to 2. Let us first assume that each participant has at least one friend among all the participants of this cocktail party. Then our boxes or containers correspond to the number of friends. Each participant has at least one friend, so our containers are 1, 2, and so on up to k minus 1. So we have k minus 1 containers. Using the pigeonhole principle, we get that there are at least 2 people, because we have k people, which is strictly greater than k minus 1. At least 2 people will be in the same container, so we'll have the same number of friends. Now let us assume that one of the participants has no friends. But this means that no participant can have k minus 1 friends. So now our containers, which correspond to the number of friends, are 0, 1, 2, and so on, all the way up to k minus 2. So again we have k minus 1 containers. So using the pigeonhole principle, since the number of items is strictly greater than the number of containers, we conclude that there are at least 2 people with the same number of friends. Here is one more example. Example 4. In any group of 6 people, there will either be 3 people who know each other or 3 people who do not know each other. We assume that to know someone is a symmetric relation. If X knows Y, then Y knows X. So let P be one of these 6 people. By the pigeonhole principle, out of the remaining 5 people, there are 3 or more, say X, Y, and Z, such that P either knows all of them or doesn't know all of them. Why? So we have 5 people apart from P, and P can know each of them or do not know. So we have 2 containers, knows, doesn't know, and 5 people. So we put 5 people in 2 containers, at least one container contains 3 people. Great, so we pick X, Y, and Z, and consider first the case where P knows X, Y, and Z. So if any of these X, Y, and Z knows any other of them, let's say X knows Y, we have 3 people, P, X, and Y, who know each other. Great. If X, Y, and Z do not know each other, we have 3 people who do not know each other. Great. Again, we are done. The second case is similar. If we assume that P doesn't know X, Y, and Z, if any of X, Y, and Z doesn't know any other of X, Y, and Z, so let's say X doesn't know Y, then P, X, and Y do not know each other. And this was what we wanted to show. And finally, if X, Y, and Z know each other, so here we have 3 people who know each other. And we are done, so this example is also completed. Now let's go into the direction of binomial coefficients, and let's first start talking about combinations. So let k be a non-negative integer. Consider the set B of k underlined of all subsets of the set k underlined. Recall that k underlined is a set of all integers between 1 and k. 1, 2, 3, and so on, all the way up to k. We know that the cardinality of the set of all subsets of a set with k elements is 2 to the power k. Subsets of k underlined can have cardinalities between 0 and k. So let's pick some possible cardinality m between 0 and k, and denote by b of k underlined m the set of all subsets of k underlined of cardinality m. So for example, B3 underlined 2 consists of the following 3 subsets of 1 to 3. So we have 1, 2, 2, 3, and 1, 3. These are all 2-element subsets of the set 1 to 3. So subsets of k underlined are sometimes called combinations, and so B k underlined m is the set of all m-element combinations out of k available elements. Now we can define binomial coefficients. We denote by the following symbol. This symbol is usually read as k choose m, the cardinality of the set B of k underlined m. So the number of m-element subsets of a set with k element is denoted by this symbol, which is usually pronounced as k choose m. And these kind of symbols are called binomial coefficients. Why will be clear from the next slides. Alternative notation are C sub k upper m or C sub m upper k or C sub k comma m, and there are many others. So here C means combinations. So for example, if we take k to be equal to 3, then k underlined is 1 to 3. There is a unique subset of 1 to 3 of cardinality 0, and that's the empty set. So 3 choose 0 is equal to 1. There are 3 singleton subsets of 1 to 3. So these are 1, 2, and 3. So 3 choose 1 is 3. As we already saw in the previous slide, there are 3 2-element subsets of 1 to 3. These are 1, 2, 2, 3, and 1, 3. So 3 choose 2 is equal to 3. And finally, there is a unique 3-element subset of 1 to 3. It's 1 to 3 itself. So 3 choose 3 is equal to 1. Let's write down a formula for this binomial coefficient k choose m. Theorem: k choose m equals k factorial divided by m factorial times k minus m factorial for any m between 0 and k. Proof: let us choose an ordered sequence of m elements out of 1, 2, 3, and so on k. We can choose the first element in k different ways. Any element will work. We can choose the second element in k minus 1 different ways because the first element is already taken. One element disappeared. We can choose the third element in k minus 2 different ways, and so on. And we can choose the mth element in k minus m plus 1 different ways, as m minus 1 elements are already taken. So using the rule of product, since all this is independent, using the rule of product, it follows that we can choose an ordered sequence of lengths m of different elements from k underlined in k times k minus 1 times k minus 2 times and so on times k minus m plus 1, which is equal to k factorial divided by k minus m factorial different ways. Now we remark that subsets differ from ordered sequences exactly in that subsets do not have any order on the elements of the subset. And at the same time, so we have now an ordered sequence of m elements, and we want to compare it to a subset with m elements. We know that m elements can be ordered in m factorial different ways. Therefore, this number which we have, k factorial divided by k minus m factorial, that's an overcount, where each subset is counted m factorial times. So hence the final answer is that our binomial coefficient k choose m equals k factorial divided by the product of m factorial and k minus m factorial. Now we can formulate the so-called binomial theorem, which is the source of the name binomial coefficients for our numbers k choose m. So for a non-negative integer k and two variables x and y, we have that x plus y taken to the power k can be written as a sum over all m from 0 to k, the coefficient k choose m times the monomial x to the power m, y to the power k minus m. Proof: let us compute x plus y to the power k, which is a product of x plus y times and so on, where we have k factors, by opening the brackets using distributivity between product and addition. So to get a monomial of the form x to the power m, y to the power k minus m, so we need to choose m summands of the form x from m of these k factors, and we need to choose from all the remaining factors, we need to choose y. Therefore, by the rule of bijection, the coefficient at x to the power m times y to the power k minus m equals the number of m element subsets of a set with k elements. That is exactly the binomial coefficient k choose m. Here are some observations. Observation 1, which is just a special case of the binomial theorem, we have that 1 plus x to the power k equals the sum over all m from 0 to k, and then the coefficient k choose m times x to the power m. So to get this, we just evaluate the binomial theorem at y equals to 1. Observation 2, m factorial divides the product k times k minus 1 times k minus 2 times and so on times k minus m plus 1. So indeed, if we take this product and divide by m factorial, we will get exactly the binomial coefficient k choose m, which is an integer, as we know, because it counts something. Observation 3, the binomial coefficient k choose m equals the binomial coefficient k choose k minus m. Indeed, k choose k minus m equals k factorial divided by k minus m factorial times k minus m and the whole thing factorial. This is equal to k factorial divided by k minus m factorial times m factorial, because k minus m equals m. And this in turn equals the binomial coefficient k choose m. Next, let us establish the most useful recursion formula for the binomial coefficients. For any m between 1 and k minus 1, we have that k choose m equals k minus 1 choose m plus k minus 1 choose m minus 1. Proof. Let us just use our formulas and compute k minus 1 choose m plus k minus 1 choose m minus 1. K minus 1 choose m equals k minus 1 factorial divided by m factorial, k minus 1 minus m factorial. And k minus 1 choose m minus 1 equals k minus 1 factorial divided by m minus 1 factorial times k minus 1 minus m minus 1 factorial. So we multiply the numerator and denominator of the first summoned by k minus m and of the second summoned by m to get to the common denominator. The common denominator will be m factorial times k minus m factorial. And then the numerator of the first summoned is k minus 1 factorial times k minus m, and the numerator of the second summoned is k minus 1 factorial times m. And this m and this minus m, they cancel, and then the common numerator simplifies to k factorial, so the whole thing equals k factorial divided by m factorial times k minus m factorial, which is k choose m. And this completes the proof of our proposition. Let us note that if n is equal to 0 or m is equal to k, then k choose m is equal to 1. In particular, if k is greater than 1 and m is equal to 0, then k choose 0 is equal to k minus 1 choose 0. While if k is greater than 1 and m is equal to k, then k choose k is equal to k minus 1 choose k minus 1. So our formula simplifies with only one summand and the second one is 0. Consequently, if we define k choose m to be equal to 0, provided then m is not between 0 and k, then this formula is valid for all integers k and m, except for the special case where k is equal to m is equal to 0. Using this formula, we can draw a very nice picture with binomial coefficients, which is known as Pascal's triangle. So we arrange our binomial coefficient on a two-dimensional grid as follows. So the rows of this grid correspond to the values of k. K is equal to 0, k is equal to 1, k is equal to 2, and so on. And then we draw for k is equal to 0, we only have 0 choose 0. For k is equal to 1, we have 0 choose 0 and 0 choose 1, and so on. So the value of m here goes diagonally, so this diagonal is m is equal to 0, this is m is equal to 1, and so on. And here, in this grid, any number is equal to the sum of the two numbers immediately to the northwest and northeast of it. So 1 is equal to 1, and here we have 0. 2 is equal to 1 plus 1, 3 is equal to 1 plus 2, 6 is equal to 3 plus 3, and so on. This is one very easy way to compute and draw binomial coefficients in this kind of triangular array. This is known as Pascal's triangle. Let us now also give a bijective proof for our recursive formula that k choose m equals k minus 1 choose m plus k minus 1 choose m minus 1. Consider the set B k underlined m, the set of all m element subsets in 1, 2, 3, and so on k, and we know that this is enumerated by the left-hand side of our equality, which is k choose m. Let us split our set into two disjoint subsets, let's call them A and B. Here A contains all elements in bk underlined m that contain the last element k. And B contains all elements in bk underlined m that do not contain the last element k. Clearly from the definitions, the intersection between A and B is empty, and the union of A and B is exactly our set B, K underlined M. So by the rule of sum, the cardinality of B, K underlined M equals the cardinality of A plus the cardinality of B. So we need to prove that the cardinality of A and the cardinality of B are given by our summands on the right-hand side of the formula we want to prove. So let us analyze this A and B separately. For an element capital X in A, so that's a subset of 1, 2, 3, and so on K, which contains K. If we remove this K from X, we get a subset of 1, 2, 3, and so on K minus 1 with M minus 1 elements. And conversely, if we have a subset from K minus 1 underlined with M minus 1 elements, we add K to it and we produce an element in capital A. And this gives us a bijection between A and B of K minus 1 underlined M minus 1. So in particular, the cardinality of A equals K minus 1 choose M minus 1 due to the rule of bijection. Next, any element Y in B that's a subset of 1, 2, 3, and so on K, which does not contain K. So in fact, it's a subset of 1, 2, 3, and so on K minus 1 with M elements. So it belongs to B, K minus 1 underlined M, and vice versa. So B actually is equal to B, K minus 1 underlined M. So in particular, the cardinality of B is K minus 1 choose M. So we add the cardinality of A to the cardinality of B, and we exactly get the formula which we wanted to prove. Some examples illustrating how one can use binomial coefficients. Problem 1. How many 5-digit positive integers have their digits in the strictly increasing order? Solution. We are looking for positive integers of the form a1, a2, a3, a4, a5, such that a1 is smaller than a2, is smaller than a3, smaller than a4, smaller than a5. Note that a1 is greater than or equal to 1 because when we write a 5-digit integer, we start from a non-zero number. And in particular, all ai's are non-zero. And so such a number is uniquely determined by a subset of 1, 2, 3, 4, 5, and so on 9, consisting of 5 elements. So by the rule of bijection, the number of our 5-digit positive integers with strictly increasing digits equals the cardinality of 5-element subsets in a 9-element set. So the answer is 9 choose 5. Problem 2. There are 20 males and 15 females in a room. From these, one has to create 5 pairs for a tango competition. A pair should consist of 1 male and 1 female, and there is no ordering on the pairs. They are not ordered inside or between each other. In how many different ways can one do this? Solution. So we need to choose 5 males which will take part in the competition. We have 20 males, we can choose 5 of them, is in 20 choose 5 different ways. We can choose 5 females out of 15 that are present, in 15 choose 5 different ways. So now we have 5 males and 5 females, and we need to create 5 pairs, 1 male and 1 female in each. So this can be done in 5 factorial different ways. So now we use the rule of product and get that the answer to our problem is 20 choose 5 times 15 choose 5 times 5 factorial. Problem 3. For positive integers k and m, determine the number of non-negative integer solutions to the following equation. x1 plus x2 plus and so on plus xm is equal to k. Solution. We visualize the solution a1, a2, and so on am to this equation as a 0-1 sequence as follows. We start on the left with a1 zeros. Then we write a 1, indicating that a1 is now finished. Then we continue after this 1 with a2 zeros. Then we write another 1, indicating that a2 is finished, and so on. A general convention, we ignore the very last 1 after am because it doesn't provide any additional information. So we have k zeros and m minus 1 ones. So for example, the sequence 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0 corresponds to the solution 2 plus 1 plus 0 plus 3 plus 1 is equal to 7, to the equation x1 plus x2 plus x3 plus x4 plus x5 is equal to 7. So, from a solution to our equation, we obtain a 0, 1 sequence of lengths k plus m minus 1 with k zeros, or equivalently with m minus 1 ones. Conversely, if we have a 0, 1 sequence of lengths k plus m minus 1 with k zeros, we can uniquely read off the sequence as solution to our equation by reversing the above procedure. Hence, there is a bijection between solutions to our equation and 0, 1 sequences of lengths k plus m minus 1 with k zeros. So the answer to the problem is k plus m minus 1, choose k. Or equivalently, we can write it as k plus m minus 1, choose m minus 1. So this is the number of non-negative integer solutions to that equation. There is a generalization of binomial coefficients, which is called multinomial coefficients, which we briefly discuss at the end today. So for non-negative integers k1, k2, and so on, km, define k1 plus k2 plus and so on plus km, choose k1, k2, and so on, km, this kind of symbol as k1 plus k2 plus and so on plus km factorial divided by k1 factorial, k2 factorial, and so on, km factorial. Note that a plus b choose a comma b is equal to a plus b choose a. So on the left-hand side we have the definition as we see here, and on the right-hand side that the usual notation for the binomial coefficients. It is a little bit confusing, but that's what is traditionally used. These numbers k1 plus k2 plus and so on plus km, choose k1, k2 and so on km are called multinomial coefficients because they appear in a generalization of the binomial theorem, which is called multinomial theorem, which we will present now. So we have the multinomial theorem. For a positive integer m and a non-negative integer n, we have the following expression. x1 plus x2 plus and so on plus xm to the power n can be written as a sum taken over all k1, k2 and so on km, non-negative integers which add up to n, and then we have this coefficient n choose k1, k2 and so on km, and send the monomial x1 to the power k1, x2 to the power k2 and so on xm to the power km. And the proof of the theorem is a nice exercise which uses binomial theorem and induction on m. So here's an example for three variables x plus y plus z. So x plus y plus z to the power 3 equals x cubed plus y cubed plus z cubed. And then we have many summands with coefficient 3, namely 3x squared y plus 3x squared z plus 3y squared x plus 3y squared z plus 3z squared x plus 3z squared y, and then the remaining summand plus 6x, y, z. Additional problems and questions at the end. Problem question 1. Prove that for k greater than or equal to 0, we have that the sum of all binomial coefficients k choose m equals 2 to the power k. Problem question 2. Prove that mapping x to k underlined minus x defines a bijection between b k underlined m and b k underlined m minus k, and deduce from this that k choose m equals k choose k minus m. That's a bijective proof for this equality. Problem question 3. How many 5-digit positive integers have their digits in the strictly decreasing order? Problem question 4. Prove that for n greater than or equal to 0, the sum over all k1, k2 and so on km, non-negative integers which add up to n, of the corresponding multinomial coefficients n choose k1, k2 and so on km, equals m to the power n. And problem question 5. For positive integers k and m, determine the number of positive integer solutions to x1 plus x2 plus and so on plus xm is equal to k, to this equation. Thank you very much and see you next time.